So now that we've looked at the vibrational energy spacing for a simple harmonic oscillator, and we've shown that in spectroscopy the selection rule is you go from some quantum number v to v plus 1, which is typically from 0 to 1. So we step by one step, and for a harmonic oscillator, that step's always exactly the same size, a perfect ladder with separation nu e. But then we drew a bond, and it's not a parabola. It doesn't go on forever. And so there's this thing called anharmonicity. And we're going to treat the anharmonic oscillator. And the basic idea is that the term symbol, remember we call the energy levels in spectroscopy, we call it a term, and we use big G to indicate that. G of v plus a half, the quantum number plus a half, is equal to v plus a half times nu e, nu twiddle e, the characteristic wave number of the oscillator, minus now a term that goes like v plus a half squared times this thing we call xe nu e. And xe nu e is what we call the anharmonicity. And this is a classic Taylor series. So I've got a term that's linear in this variable, which in this case is the quantum number, v plus a half. And then there's a term that's quadratic, and we expect that xe nu e is going to be quite small compared to nu e. In other words, xe is going to be a lot less than nu e. And so if nu is 1,000 wave numbers or something like that, we expect xe nu e to be a few wave numbers. So xe is going to be something on less than 1% or something like that. So it's a very small number, but spectroscopy can measure light frequency to extraordinarily high precision, and so it does matter, and it matters in a lot of ways. So the main thing is we notice that minus sign there. So it means the levels, the energy levels, are getting lower due to this anharmonicity. And the reason is because, remember, the presence of levels in a quantum system depends on confinement. So what's going on is as I break the bond, I'm pulling this thing apart from being a parabola. The confinement is less. When I have less confinement, a given wave function will have less curviness to be confined, and so the kinetic energy goes down. So pulling a system apart tends to make the energy go down, and that's represented here. So the 0-point energy of this system now comes from putting the vibrational quantum number 0 in there. So we get G of 0 plus a half, v plus a half when v is equal to 0 is 1/2. Now nu e minus 1/2 xe nu e. And so essentially the characteristic, if you will, remember that the 0-point energy was 1/2 nu e for the simple harmonic oscillator, and now it's a scooch lower, and it's by 1/2 of this anharmonicity taken off the characteristic frequency. Now for spectroscopy we care about energy differences, so delta G of v plus a half is equal to G of v plus a half plus 1, that's the final quantum state, minus G of v plus a half, that's the initial quantum state. And without further ado, if you work out the math, which is done in the notes, this comes out to nu e minus xe nu e minus 2 times v plus a half times xe nu e. So the characteristic separation is again a little bit less, because what's happening is each and every step in this oscillator is getting lower and lower and lower and lower compared to that characteristic nu sub e every additional vibrational quantum number. So it starts out a little bit lower, and then it gets lower and lower and lower because it goes like 2 times v plus a half times this anharmonicity. So if we look at the typical transition, which is from 0 to 1, that's delta G of 0 plus a half, and that's just equal to nu sub e minus twice xe nu e if you work it through. So the very first step you can take in the anharmonic oscillator has an energy separation between v equals 0 and v equals 1 that is rather lower than it would have been if the system were truly harmonic. And that nu e, by the way, that comes from the curvature, the second derivative of the potential, right smack at the bottom, down where it's actually equal to 0, and at the minimum where the second derivative is the only important derivative of the thing. So the curvature right down there at the bottom. But because the 0 point extends beyond that equilibrium distance, because of the 0 point displacement, the wave function, if you will, samples some space away from that equilibrium point, and that's why, again, it gets a little bit wider, and thus the curviness is a little bit lower, and with lower curvature, you get a lower kinetic energy, and the energy drops just a little bit on the ground state there. For the Morse oscillator, first of all, this term, this anharmonicity, it's often expressed just as xe. That's equal to the equilibrium, nu e, divided by 4 times the equilibrium bond energy, dE, of the Morse oscillator. We can multiply by nu e to get xe nu e is equal to nu e squared divided by 4 times that equilibrium bond distance. So the anharmonicity is actually directly calculated, and in fact, this term above, with the second order Taylor expansion, that just is v plus a half times nu e minus v plus a half squared times xe nu e, those are the exact energy levels for this Morse oscillator, which is one of the reasons that I kind of like to use it, because we won't deal with the exact wave functions. If you think way back, they're actually harder to find. They look just about like the simple harmonic oscillator wave functions anyway, but the energy levels are somewhat lower, and we'll look at that more in just a second. I want to look at the Morse potential a little more quantitatively as well. And these are figures that are in the notes, so we're just going to talk them through. So this figure here shows what a typical Morse oscillator looks like. We have on the x-axis the bond distance in angstroms here. And this is drawn for a bond of a characteristic of 1 angstrom, and we've got a energy here in wave numbers, and we got 30,000 wave numbers, so 3, and there's a times 10 to the 4th up here. That's the way MATLAB tends to like to indicate these things. And this gives you a sense for what the energy landscape of an actual typical chemical bond looks like. This would be a typical single bond for a Morse oscillator, but it's a pretty good match to a lot of functions. So here's our angstrom, and then it's only 0.8 angstroms over here on the left-hand edge. The function's getting huge, and we pull out to 1.2, 1.4. By the time we're at 1.8 angstroms, this thing's completely gone. So it's been ripped apart, and the function's almost completely flat over there. So then the important thing that we mentioned earlier is that the important quantities in here are, first of all, you can't get down perfectly to the equilibrium bond distance. Now we've changed coordinates a little bit here. This is actually for HBr. So this is the best estimate Morse oscillator for HBr. I've zoomed in a little bit, so 4 angstroms is the maximum distance we go out here. The HBr equilibrium bond dissociation energy, which is from the 0 here, the very bottom of this well of this oscillator, at about 1.4 angstroms, all the way up here is about 38,000 wave numbers, so 3.8 by 10 to the 4 there, this black line. That's from the very bottom of the well all the way up. So that's the equilibrium bond dissociation energy. It's the bond dissociation energy we could have if the system actually could sit down there right down at the bottom. But it's a classic case of quantum confinement, and instead the lowest energy solution you can get is this red line here. That's the V equals 0 solution for this harmonic oscillator for HBr, where you can pack that in, and the curviness of that wave function is appropriately balanced, so the kinetic energy that the solution has is proportional to the confinement, and it settles in there at this 0 point. That's as far down as the system can settle in. So that difference between the red line, the horizontal red line, the energy there, and the bottom of this well that we define as V equals 0, that's the 0 point energy. And the 0 Kelvin bond dissociation enthalpy, D naught, that you can look up in chemical tables, that is the difference between this equilibrium bond dissociation energy, dE, which is essentially the intrinsic depth of this well, and then this 0 point energy that's a function of the oscillation. That is the 0 Kelvin. It's the lowest energy you can possibly have. At 0 Kelvin, every single one of the HBRs will be in this ground state, but you can't push them farther down. And that's really the critical issue here. And to give you one of several examples of why this matters, we will see later how we can use quantum chemistry to actually calculate things like this blue curve. So we can actually calculate how tightly molecules are bound together, the second derivative of the surface that gives us the force constants, that gives us the frequencies of the system, everything, we can calculate that. But we're calculating the blue curve. We then have to go and figure out what the red line is, what the 0 point energy is, in order to get the actual prediction of this bond dissociation enthalpy d naught. So you've got to do them all. Now with the Morse oscillator, the actual energy levels for HBr, they look like this, right? So this is kind of cool. There's the V equals 0 case that we were just looking at. There's V equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. There might be a 28, it's hard to tell. You see, they get really close together at the top. There's actually a finite number of them. And so when you see, you kind of can climb out of this well by going from one vibrational state to another. And you can actually do that. There are ways that you can dissociate molecules actually doing that. But you see how they really do get close together. They start out looking more or less evenly spaced at the bottom, because this thing is more or less a parabola at the bottom. But then as I start to pull the system apart, as we get out here in this part here where the blue potential energy curve really curves over, and I'm starting to really crack and break that bond, then the system really spreads out. And as it spreads out, that's remember that in the particle in the box, the energy levels go like 1 over L squared. So as I increase the size of the spacing, that's going to pull the energy levels down again, because there's a greater distance. If I have a given number of nodes, the wavelength is longer between those nodes because I have a larger spacing. Energy goes like momentum squared in general. The curvature that I'll put into that, the curviness, is going to give me a relatively lower kinetic energy, and the spacing gets lower. So this is the distribution of states. And again, for the Morse oscillator, this is actually exact. Those are exactly where the energy levels would be if HBr were precisely a Morse oscillator, as you start to rip the hydrogen off of the bromine, which it isn't quite, but it's not such a terribly bad example. Just like we did in the other example of the harmonic oscillator, we're returning to the carbon monoxide as an example as we look at the Morse oscillator. And this is in the Chapter 8 notes. It's section 8.4.1.1 under carbon monoxide. And the key features are shown here in this graph. Now, remember, we have this triple bond, and so instead of 30,000 wave numbers being the bond strength, this is up to 90,000 wave numbers. So in fact, 91,062 wave numbers is the bond strength, and the equilibrium bond energy is 21,000. The equilibrium frequency, is 21,070 wave numbers, and that gives the. You can also solve that for Xe Nui as we showed the anharmonicity, and you get 12.9 wave numbers out of the deal. So again, I mentioned that the anharmonicity would be of order a fraction of a percent. Here it's about 0.5% of the fundamental frequency. So it's a small number, but the characteristic numbers, as you can see here, we've got the 90,000, 91 and 62 wave numbers, 91,000 and 62. Then the 2170 wave numbers is the spacing between these two red lines, more or less, until we account for the anharmonicity. The 0 point energy is going to be something a little over 1,050. 1,085 would be the harmonic 0 point energy right there. And then we're going to have a little ground state wave function, and it's this little magenta curve here. And so the particle, this carbon monoxide bond, is going to have a 0-point oscillation here about this 1.2 or so angstroms, and it's way down in this well compared to the dissociation, which is way, way, way up here. And so now what we can do is we can start to zoom in on this thing. And so let's see. Let's go in a little bit closer, and I think we look at the Morse close here. So this shows the first 3 states now, and here's the ground state wave function now, and we have coming in fairly close to the bottom of the well here. So now here's the 0-point energy, which is a little over 1,000, 1,080 or something wave numbers like that. So that's V, the energy of the lowest energy, V equals 0. V equals 1 here is up there, almost 2170 above that, and there's a little bit of anharmonicity. So this has shown, there are 2 curves here. The blue curve is the Morse function, and the black curve is a parabola that is exactly right at the bottom. So it's got the exact right equilibrium bond length of about 1.1. It's 1.12 or so angstroms, and it's also got the exact same curvature. And so you can see that for the V equals 0 solution, the black and the blue curves are almost the same. And then actually an interesting thing's happened as we go to V equals 1 here. Notice that the black on the inside, what we call the repulsive wall, the Morse curve has actually moved a little bit away from the black. So it's gone out a little bit. On the other side, as there's the beginnings of the bond stretching and breaking, the blue has also gone in the same direction. So the potential has kind of shifted, but you can tell visually that it hasn't gotten all that much wider. So there's not all that big a deal here. And you look up at V equals 3, you can see that now maybe the right-hand side here is getting a little bit wider. It's moved a little bit further to the right as you go from black to blue here than it has here, where it's moved a little bit less toward the right. But things are also beginning to shift out. And that gives you a hint that actually, as you excite the system, the bond length of the vibrationally excited modes actually does increase a little bit, and that'll come back to we'll see that show up actually next week when we deal with another interesting system here. So now let's actually look at that. We'll back up a little bit again and look at the first several, just the states now. Because we've taken the black parabola away, but you can now see the blue curve as we're looking at the first 30,000 wave numbers or so, 25,000 wave numbers. So that's 5,000, 10, 15, 20,000 wave numbers on the y-axis there. And now the dashed red lines are the energy levels that you would get from the harmonic solution. So using 2170 wave numbers exactly, if the parabolic solution were correct. The actual red lines are the energy levels that the Morse function has. So you see that the black, the red solid line and the red dashed line at V equals 0, V equals 1, and really V equals 2 almost. You can barely tell them apart. You can just see a little hint of dashing. By the time you get to V equals 2 here, a little above 5,000 wave numbers, you can start to see some separation. Above that, and the separation starts to get pretty large. So here we go. Let's see. This is 1, 0, 1, 2, 3, 4, 5, 6. Now it's the V equals 6 case. We've dropped down a not unappreciable portion of the total distance between these states. Here's 7. It's even bigger. Here's 8. By 9, the actual V equals 9 state of the CO Morse oscillator is actually kind of closer to the V equals 8 harmonic case than it is to the V equals 9 harmonic case. And the V equals 9 Morse case has almost come down to the V equals 9 harmonic case. So the anharmonicity really does start to get quite significant as you go toward very high excitations. And obviously, if you look at this function, it's not a parabola either. The non-parabolic element is large. And you can see the right-hand side of this is pulled out more than the left hand is pushed in by a rather dramatic amount by the time you get up to this v equals 9, v equals 10 level. But finally, we can zoom in about as far as we can go. We look at just the first two cases now, just to give you a sense of, again, what these wave functions actually look like. And we've actually put two things on here. So the green curves are the wave functions themselves. The magenta is the amplitude of the wave function squared, and they're real, so it's just the wave function squared. And here we have the probability distribution now of the bond length. And that's so the magenta curve is the probability distribution of the bond length here. And it's saying that there's a very darn good chance of finding the bond between 1.17 and 1.23 angstroms or something like that. If you excite to v equals 1, you get one of these funny quantum things where the probable bond distances are either something around 1.15 plus or minus 0.1 or something like that, 0.01. Or it can be over here at something like 1.25 or something like that. But the probability of finding right in the middle is vanishingly small. So if you were able to excite all the carbon monoxides with an infrared laser and put them all equal to v equals 1, you'd have this really interesting probability distribution of the equilibrium bond length. And so we can work through, and you can pull the constants for basically any molecule and get this whole range of solutions precisely and exactly for the Morse oscillator case. So this is now starting to tell us very much real things about the way real molecules behave.